In this lesson, we'll continue our discussion on big idea number 1, talking about energy changes and how they can be described quantitatively. And we'll tackle learning target number 3. So by the end of this lesson, you should be able to describe Hess's law and discuss when it is used. You should be also able to calculate the enthalpy change of a reaction by combining chemical equations algebraically and by using the enthalpies of formation method. Hess's law states that the enthalpy change of a physical or chemical process depends only on the enthalpy of the original reactants and the final products. It is independent of the pathway or the number of steps in the process. So why would we need to use Hess's law? It allows us to overcome limitations of calorimeters. And sometimes it even lets us find the enthalpy change without doing an experiment. Now, here's an example of Hess's law. You can make CO2 in a one-step process. Burning carbon and excess oxygen, you make CO2, which has an enthalpy change of minus 393.5 kilojoules. Or you could make CO2 in 2 steps. You could take carbon and make it your excess reactant and burn it in a little bit of oxygen and make carbon monoxide. That's exothermic to the tune of 110.5 kilojoules of energy. Then if you take that carbon monoxide and burn it again in lots of oxygen, you can change that into CO2, which has an enthalpy change of minus 293.0 kilojoules. If you add those two enthalpy changes together, you'll get minus 393.5 kilojoules. Like Hess's law states, it doesn't matter how many steps it takes to get from reactants to products, the enthalpy change of the overall reaction will be the same. There are 2 different ways that you can use Hess's law to determine the enthalpy change. The first way is known as the algebraic method. You combine chemical reactions with known delta H values so that they add together and equal the equation that you want, which is known as the target. Use the following steps to algebraically add equations together. You rewrite equations so that the reactants and the products appear on the proper side of the target equation. If you need to reverse an equation, write it backwards. You have to change the sign on the delta H. You can multiply equations by a factor so that the amounts of the reactants and products match those of the target equation. If you do so, you must multiply the delta H of the equation by the same factor. Then you add the equations together. If the same chemical appears on opposite sides of the arrow, you subtract the amounts. If the same chemical appears on the same side of the arrow, then you add the amounts together. Number 4, if the sum of your chemical equations equals the target, then you've manipulated the equations properly so that the sum of their delta H's will equal the enthalpy change of your target. Here is an example. I want to find the enthalpy change for this target reaction. And I know these 2 reactions and their enthalpy changes. So step number 1, I'm going to follow along in my target and rewrite equation number 1 and number 2 so that the reactants and products appear on the proper side. Starting in my target equation, I have an Fe2O3. I look in my equations until I find an Fe2O3. Equation 2 supplies that, but it's not on the proper side of the arrow. So I'm going to write equation number 2, but I'm going to reverse it, write it backwards. Now, if you write an exothermic reaction backwards, it makes it endothermic. So I have to flip the sign on the delta H value. My next reactant is a carbon monoxide. Equation number 1 has carbon monoxide in it, but it doesn't have the right amount. So I'm going to fix that by writing reaction number 1 and timesing it by a factor of 3. If I times the equation by 3, then I have to times the enthalpy by 3. Following on in my target equation, I need 3 CO2s. Equation number 1 supplies that. And I need 2 Fe's. That's taken care of by equation number 2. Let's algebraically add these two equations together. Notice that oxygen appears in both equations, in the product side here and in the reactant side here. And because they are in the same amounts, they will cancel each other out. If I make 1.5 O2s, but then use 1.5 O2s, my net amount of O2s is 0. Any chemical that appears on opposite sides of the arrow subtract each other. Any chemicals that appear on the same side of the arrow add to each other. Nothing else appears twice. I write what I have left. This equation matches my target. That means I've manipulated equation 1 and 2 correctly so that if I add my enthalpy changes together, then I will get the enthalpy change for my target equation. That equals minus 24.8. Try example 2 on the next page. Pause the video until you get your answer. Here's the answer for example 2. It's a tough one. In order to get the two H3BO3s in my target equation, I'm going to take reaction number 1 and I'm going to times it by 2. That gives me a delta H of minus 0.04. Now, in order to get the B2O3, I'm going to take equation number 3 and I'm going to divide it by 2, or I'm going to times it by a factor of 1/2. If I divide the equation by 2, then I need to divide the enthalpy by 2. That gives me 8.75. Now if you look at the target equation, there's no H2B4O7, but unfortunately here I have half a mole. I'm going to use equation number 2 to get rid of it. If I take equation number 2, and if I reverse it, that will get the H2B4O7 on the product side, so it will cancel out the same chemical in equation number 3. Now to make it the same amount, I also have to divide it by 2. This will also help fix the amount of waters that I have. Right now, I only have 2.5 on the product side. So this reaction, I reversed it. So that means I need to flip the sign on my enthalpy change. It now becomes positive. And then I also need to divide it by 2. Let's see if these equations algebraically add together. I have two HbO2s. Here is a product, here is a reactant, and they're the same amount, so they will cross each other out. Because they're on opposite sides of the arrows, they subtract each other. I also have half of an H2B4O7 as a product and half as a reactant, so they also cancel each other out. And I also have multiple waters. They are all on the product side, so they will add together. 2, 2.5, 3, which is good, because that's what's required in my target. Because my 3 manipulated equations add to my target, that means my 3 manipulated enthalpies will add to the enthalpy change of this target equation. This gives me a positive 14.4 kilojoules.